Hey, welcome back to your favorite, favorite calculus class. Good to see you guys. Talk to you guys, I guess, right? Well, we'll see if we can't make this work here. We're going to continue on with monotonic functions and the first derivative test. Let me get my pen here as well. Let me move this on here. Let's talk for a minute about increasing and decreasing functions. So if you remember, increasing means if x1 is less than x2 on an interval from x1 to x2, if f of x1 is always less than f of x2, you're going to be increasing, right? So for example, with this one here, you got x1 less than x2, and f of x1 is obviously lower than f of x2, right? So we're increasing, going up and to the right, increasing. We're constant if we're staying the same y value. If f of x1 is higher than f of x2, of course, we're going to be decreasing. And that first derivative test tells us, about this. We discussed that first derivative test. This is saying, if this is A, that's B, critical numbers. Our slope here, the slope of the tangent is always going to be negative. So we know that function will be decreasing until A. Of course, in between here, it's just constant, so f prime is 0, so this is not the greatest example. But after here, between here, f prime is 0, so this thing's staying constant that whole time. And here, you got all your slopes of the tangents are all positive, so the function is increasing after that. That's all that is saying here. So let's look at using the first derivative to examine and to kind of get a feel for the graph of this x cubed minus 3 halves x squared. So let's go ahead and take the derivative here. We got 3x squared minus, what's that? 3x. Let's go ahead and set that equals 0. Let's factor out a 3x. So we've got 3x being 0, x minus 1 equals 0. So we've got critical points 1 and 0. So critical points are, again, any point where the derivative is 0 or where the derivative is undefined. Now, it's only considered, technically speaking, although you put them both on the graph, even if it's undefined, you want to analyze around it. But let's say that f prime of 1 was not defined, then it's not, technically speaking, a critical point if you're doing your homework. Okay, but you do want to analyze around it. So you want to put it on the first derivative test to test around it. Okay, now we're going to go ahead and take the derivative, -1. So we're going to plug it into our first derivative here, the 3x, our f prime here, f prime of x. Oops. I'm going to put it into that factored form. So we got 3 times -1 times -1 minus 1. So we got -3 times -2. So we got 6. What's important is it's positive. That means the function is increasing because the slope of the tangents are positive on that interval that whole time, right? So it's increasing. Now we're going to throw in like a half. So I got 3 times a half. I got 3 halves. Half minus 1. So this equals 3 halves times a half. Half minus 1. Again, I'm plugging it into here, right? Negative a half. So we got -3/4. So what's important is this is negative. F prime of 1/2 is negative. That means all slopes of the tangents are negative, so the function must be decreasing. Now I throw in f prime of 2. I get 3 times 2, 6 times 1, so I get 6. So f prime of 2 is positive, so the function is then increasing. So we can kind of get a feel for this graph when you consider this first derivative test, as well as you want to think about your end behavior. This is a third degree, so it's an odd function. So it's going to either behave kind of like at the endpoints at least, kind of like x cubed or negative x cubed. Well, this has a positive leading coefficient of 1. So at the extremities, it's going to go up to the right, down to the left. So you want to kind of keep that in mind, your end behavior, as you're also plotting some points here. So you want to plot your critical points. Those are defined. So 0, 1. You want to plot some to the left, plot some in between, plot some to the right, as many as you need. So I'll plug in, let me plug in my critical points through first. I throw in 0 and I get 0. I throw in 1 and I get 0, 3. I'm sorry, I'm throwing it in to my original here. 1 cubed 1 minus 3 halves. So I got 1 minus 3 halves, -1/2. And you can plug in watch these other ones like -1 ends up being 5 halves. You got -2, so -14. Plug in a half cubed minus 3 halves times a half squared. You're going to get 4. Plug in the 2 and you got 8 minus 3 halves times 2 squared. So 8 minus, you got 2. Plug in the 3, you got, what's that, 13. 7 halves. 7 minus 27 halves, yeah. 27 halves, perfect. And so now we're starting to think about this graph here. So we're like, well, I got this -2. Anyways, clear down here, -14. We know it goes down to the left, and we also know it goes up and to the right. We're hitting 0, 0. Come on. 0, 0. We're also hitting 1 comma -1/2 right there. Yeah, putting these points on -1, -5 halves. So down 2.5 right there. What is struggling to read this thing? -2.5. There we go. Put the point on 0, 0. We got 1/2 comma -1/4, 1 comma -1/2, and we know this thing is increasing until an x value of 0, because the slope of the tangent here is 0. So we got right here at x being 0, so since it increases and then decreases, we got a relative max right here, relative max. Then it goes down, hits that point, hits the 1 comma -1/2. Now it decreases and then increases, so we got a relative min right here at the 1 comma -1/2, and then it turns the corner. We hit 2, 2. Anyways, we keep hitting it, and we kind of draw the rest of this. We know it goes up and to the right, and we can draw the rest of those points. But again, we got the relative max there. We got relative or local min right there. This is the local max or relative max. Okay, there's a little better picture of it. We increase, slope of tangent there, 0, slope of tangent 0, so we decrease in between, and then we get an increase after that. All right, so let's get into some more of these examples, and let's talk about monotonic functions. First of all, a function that's strictly monotonic means it's increasing on the entire interval of study that you're looking at, or decreasing on the entire interval. This one is x cubed, and if you notice, the derivative slope of the tangent is always positive, and then slope is 0 here, but then it stays increasing. The slopes of all these tangents are positive, right? So it increases and then it increases, your first derivative test. Since it increases and then it continues to increase, this thing is strictly monotonic. If it had turned, right, if it had increased and then decreased type of deal, it would not be monotonic. All right, this one is not monotonic. It increases, but then it goes constant for a while. And then finally increases. Again, it's got to stay increasing or stay decreasing to be monotonic. This one, again, not monotonic. And we talked about this being the relative max, right? It increases up to there, and then we had that relative minimum because it decreased and then followed by increasing. Right there, bottom, top of the mountain is a max, bottom of the valley is your min, right? And this is just more discussion about that. Here's another look from an interval from A to B, where you have your lowest point, your absolute min right here. This is the lowest point at the end point. You've got f prime being 0, but there's no extremum here. It increases, but then it keeps increasing, so nothing here. But then it increases and then decreases, so we got a local max right there. Another critical point right here where f prime equals 0. We decrease and increase, so we got a relative minimum here. We increase, and then even though f prime is undefined, right, it's a point of interest on our f prime test. It increases, then decreases, and the original point is defined on the function. So we do have a max right here, and more specifically an absolute max because it's the highest point. And then we decrease and decrease, so no extremum right here, even though it's a critical point at c subscript 5. And then we got a local min if this is a closed interval. Okay. All right, let's do some more with this first derivative test. Let's go ahead and take this derivative here. We got first derivative 1/2 x, we got a half, minus derivative of the sine is the cosine. Again, set that thing equal to 0. Let's solve that. We got the cosine of what is a half. If you remember, cosine of what's a half on your, you know, look at where's your cosine of half? Well, not that one. Not at 45 degrees. It's at 60 degrees up here. Root 3/2. That's where our cosine is a half, right? It's 60 degrees or pi thirds, a rotation of pi thirds. So we know cosine pi thirds is a half. So x could be pi thirds. All right, that's one critical point. We also know if we rotate all the way around here, we have on our unit circle, we also have the point 1/2 negative root 3/2. Now, where's that at? That's your 5 pi thirds. That's your 5 pi thirds. Rotate all the way around. In other words, all but 60 degrees. Right? This is 60 degrees in here, so it's at 300 degrees. So we know cosine of 5 pi thirds is also a half, so 5 pi thirds. Now, I know like negative pi thirds also works, right? Negative pi thirds. I also know, 2 pi plus pi thirds, in other words, go around and clear there to the pi thirds again. So 2 pi plus pi thirds, in other words, 7 pi thirds. That's another one. But we're only looking between 0 and 2 pi, right? This is the 0 to 2 pi there. So that's all we're going to examine since we're only looking from 0 to 2 pi. So pi thirds, 5 pi thirds on this thing. And then we'll just plug in some points. So I'm going to throw in f prime at 0. And I'm plugging it in right here to my first derivative. So I've got the cosine at 0 is 1. So I got 1/2 minus cosine of 0. Again, the cosine, the x value there at 0 is 1. So 1/2 minus 1, negative a half. So it decreases till pi thirds. I'm going to pick something between them, like pi. All right, and I know cosine at pi is negative 1. So I got 1/2 plus 1. So this is positive. So then the function increases. Then you pick like 2 pi over here. Plug that in. I know you got 1/2 minus cosine 2 pi. Cosine 2 pi is 1. So I got 1/2 minus 1. Again, this is negative. So it decreases, right? So it decreases, and then we increase, and then the function will decrease. And we can start plotting points again to kind of get a picture of this thing. But the relative extrema here, to answer the question, well, we're going to have a local min here, pi thirds, because it decreases, then it increases. All right, the function will decrease, and then until pi thirds, and then it's going to increase up until, of course, I plot some points along the way until 5 pi thirds. That's 5 pi thirds, right? And then we decrease after that. All right, of course, I'm only looking from 0 to 2 pi anyway, so I'm going to stop right there. But you can graph. Let's see if I got a graph. There we go. There's our pi thirds right there, relative min. We got the relative max there, 5 pi thirds. Okay. All right, one more here. Let's take a look at, find the critical points here of x squared minus 3 e to the x. I'm going to think about this as a product. I'm going to run the product here. So f prime of x, so derivative of the first, derivative of e to the x is ln of e to the x, derivative first, and then, of course, derivative of x is just 1, so chain rule not applying here. Derivative first times the second, plus the first, derivative of the second. That's a 2x, a really bad 2x. Well, ln of e is just 1, so I've got e to the x squared minus 3 plus 2x e to the x over here. Let me go ahead and distribute this. So I have x squared e to the x minus 3 e to the x plus 2x e to the x. I can factor out, remember I'm going to find my critical points, but so let me factor out an e to the x squared minus 3 plus 2x, which is, let me write the standard form there for the x squared plus 2x minus 3. We factor that. All right, so I got 1. I got negative 3. Now here's the question. Where does e to the x equal 0? Well, if you're to solve that, if you're to undo e to the x, you go take the ln, right? Well, the natural log of 0 does not exist. Right? It's not even a function. Remember, here's the natural log function. It doesn't even touch x equals 0. So there is no natural log of 0. So that's out. That doesn't help you. So you just got these two critical points here. X equals negative 3 and x equals 1. So we're going to plug in something to the left, f prime of negative 4. I'm going to plug it in. I'm going to plug it in right here to my factored form, f prime. So I got e to the negative 4, get negative 4 plus 3, negative 4 minus 1. So e to the negative 4 is 1 over e to the 4th. That's a negative 1. That's a negative 5. Now remember, e to the 4th, e is just 2.718. So we got 1 over 2.718 to the 4th. That's a positive number. And then negative 1 times negative 5, that's a positive number. Remember, positive times a positive is a positive. That's all I care about is this thing is positive. I'm going to throw in something in between negative 3 and 0. Negative 3 and 1, like 0. So I got e to the 0, 0 plus 3, 0 minus 1. Anything to 0 power is 1. It looks like this ends up being negative or decreases. I'll throw in like 2 over here. And I got e squared times 2 plus 3 times 2 minus 1. And I got positive here. Increasing. So increasing, decreasing, increasing. All right, so what are the intervals on which it's increasing? Well, this thing's increasing from negative infinity up to negative 3. And it also increases from 1 to infinity. Where does this thing decrease? From negative 3 to 1. That's where this thing decreases. Right? And of course, we could plot a bunch of points. You kind of see it, right? We're increasing up until this negative 3. Then we decrease. What's the daisy? Oh, then we decrease. Let me go back. Try that again. Then we decrease, and then we increase, right? So we've got the min right here. We've got a relative or local max, right? Relative max right there. This is a local min. And actually, on this function, this is actually an absolute min. Whoops, that's min. Okay, because this has a horse on the last one. So it looks like as it goes out, it approaches 0. So this is going to be your lowest point in the entire graph. So, all right, we'll take a look at the homework. Good to have you. See you next time.